So in the previous videos, we've developed linearized longitudinal and linearized lateral equations. And from these equations, we were able to put these into an eigensolver and understand the dynamic longitudinal and dynamic lateral modes. And that's the way that they used to do this. About 70 or so years ago, as they were working through this and better understanding the mechanics of flight and the dynamics of flight. That process allowed them to break up the longitudinal and lateral behaviors of the aircraft mathematically, so they could study them somewhat independently. But in that process, we threw away some information and that can be significant. So there can be some longitudinal lateral coupling that is really important. And part of their reasoning for breaking this up was because the assumptions that they made were really not terrible assumptions, to be able to break these up. So some of these assumptions were things like that the aircraft is symmetric, right? So by assuming that, they were able to drop a bunch of terms in the inertia tensor. They also assumed very small deviations from some steady level flight type of flight path, and actually it doesn't have to be level; it could be a steady climbing flight. But by doing that, they assumed that the equilibrium point of the aircraft had no roll pitcher yaw. They dropped second order terms, so we'll talk about those in just a minute. But anyway, by doing these things, they were able to divide these somewhat complicated equations into two sets, the longitudinal and the lateral equations, and produce these 6x6 matrices that we've been seeing. And actually, because each of the matrices, or each of those developments, actually in the longitudinal equations, you have two rigid body modes that are just zero. So two of your eigenvalues are just zero. Because they knew that, they could actually reduce those 6x6 matrices down to 4x4 matrices, which were much more simple to solve. 100 years ago, when they didn't have a computer to solve these, they were solving these matrices by hand. And a 4x4 matrix is much easier to solve than a 6x6 matrix. And if they hadn't divided these up into the longitudinal and lateral matrices, they would have been solving a 12x12 matrix, which was much more difficult. Well, with today's computers, we don't care if it's a 4x4, 6x6, or 12x12. To us, it takes nearly the same amount of time to solve any of these. And so leaving it all together really isn't some computational burden for us. So there are some benefits to not splitting these up and instead looking at the package as a whole. So we're going to talk now about the longitudinal lateral coupling that we've neglected in the previous development. And in the future, I'll put together a video of how you can actually put together a solver that solves these all at the same time, longitudinal and lateral. At the same time, you're solving the whole 12x12 system instead of two 6x6 systems. But that's not the topic of this video. The video here is to focus on what we've neglected by splitting these up into, or just through the assumptions that we made in order to split these into the two different sets of equations, the longitudinal equations and the lateral equations. So to do that, we're going to step back to these fundamental equations that I've got here on the screen. So if you remember, this is Newton's second law, F equals ma. So this governs the dynamics of motion as we know it. And then this is the second equation down here. Actually, this is the general form of Newton's second law, but this has to do with the angular momentum of an object. Okay, so this is the angular momentum, and we could rewrite that like this. So we worked through this previously, how you get from Newton's second law to these equations here. So anyway, these should look familiar. Now, the one thing that I've added here, well, I guess a couple things. One of them is the addition of this H matrix, and H is our angular momentum on board the aircraft. So this can come from like propellers, or other rotors, or things like that. So this is the total angular momentum, let me just label that here. So H is angular momentum. So anyway, like I said, if you have a propeller spinning or a jet engine that is spinning, or a rotor, or even other gyroscopes on board the aircraft, those can add to this total angular momentum, and you have a component of that along the x, y, or z axes, and that's what each of these are. So H in the in the H direction here, or excuse me, X direction, the Y axis and the Z axis components of that total angular momentum. Okay, so that couples, as you should remember from your dynamics class, if you have some angular momentum and then you try to rotate that object, so you have some rotation rate P, Q, or R, then that couples and creates a moment about another axis. So that's one of the things that we've now included here is this angular momentum term. And then previously we assumed that the aircraft was symmetric, so that the inertia tensor was symmetric. And that allowed us to drop out the xy term here and the yz term here. So we actually just had the diagonal terms left, and then these corner terms here, the xz term. Okay, and that allowed us to decouple the longitudinal and lateral properties of the aircraft. Okay, so in general, there are three types of longitudinal lateral coupling that are important. Four types. So the types of coupling that we're going to discuss here fall into four categories. So the first one that we're going to talk about is inertial. Okay, and that goes back to what I was just talking about, the fact that the inertia tensor here we assumed was symmetric, so we had dropped out these terms here previously, but if we include those, you can see that there's some coupling that happens. So when would this be important? Well, it would be important anytime your aircraft is not symmetric about the XZ plane. Now, most aircraft are basically symmetric about the XZ plane, but every aircraft could be carrying more fuel in one wing than the other. The way that they're scheduling the fuel, so there could be some asymmetry in fuel there. Then you could also have some asymmetry to the external parts of the aircraft, like if you have external stores on one wing, or for example, fighter aircraft, if they've dropped armament from one wing but not from the other wing, then you can have some asymmetry in how your mass is distributed relative to that XZ plane. And so you can see then that these things start to couple. So for example, in the moment, so the center equation here is our pitching moment, right? And so we can see that if we have some XY component, so this is some asymmetric inertia, that will get multiplied by, this is our roll rate here. If we have some rolling rate, and some asymmetric component here, or some change in roll rate, excuse me, then that will create a change in our pitch rate. It gives us a pitching moment, so to speak. And so you can say the same here with YZ times our change in yaw rate, right? So those two couple to create something about the pitch axis there. So that's an example of inertial coupling. Now, another place that this shows up actually is over here on the right-hand side. So this YZ term, for example, we had dropped in our previous development because it was symmetric, but that will show up, and we'll talk more about these types of terms here in just a second. And then we also have this XY term, and let's see, we've got a YZ term right here and an XY term here, YZ term, XY term. So anyway, all of these are these coupling terms that are taking some of this non-symmetric inertia. Remember the XY terms and the YZ terms. Those are the non-symmetric portions of the inertia tensor, and those show up multiplied by our rotation rates and create moments about different axes. So that's one type of coupling that we've neglected. Another type of coupling here, the second one that we're going to talk about, is gyroscopic. Gyroscopic coupling. So that comes from this tensor here. So this is our angular momentum that is that contains the angular momentum on board the aircraft due to gyroscopic effects. So, the rotating propellers or rotors or other things. Okay, so let's look at what this would look like for a typical aircraft. So let's start with a propeller. Let's say that we've got an aircraft with a propeller that, and I'll just circle these here. So that means that we have a lot of angular momentum about the x-axis. Usually those propellers are very closely aligned with the x-axis. So let's say we've got h sub x here, and now we can see that if we if we have some yaw rate, so that's r here. Remember, r is our yaw rate. If we yaw the aircraft right or left, the fact that we have this rotating propeller is actually going to create a moment about the y-axis. It's in this equation right here. So this is our center equation. This is the moment about the y-axis, the second equation down here. And so this angular momentum about the x-axis multiplied by our yaw rate will create a pitching moment. Likewise, a angular momentum about the x-axis multiplied by our pitch rate will create some yaw. Okay, so this shows that pitch and yaw are coupled for propellers. So let's just put that down here. So gyroscopic for traditional propellers, we're going to have some pitch yaw coupling. Okay, so now let's look at I'm going to call them rotors, and this is rotors would be like a helicopter rotor, right? So rotors like that helicopters have a lot of angular momentum about the z-axis. So let's put that there, and you can see our h sub z there. So let's look at this top one. So if we have some angular momentum about the z-axis, and we have some pitch rate q, that's going to create a moment about the roll axis here. Okay, so we've got some pitch roll coupling there. And likewise, if we have some angular momentum about the z-axis multiplied by a rolling moment, or rolling rate, excuse me, that will create a pitching moment. That's in the pitch equation here. So for these rotors, we're going to get roll pitch coupling. Okay. So so those are some examples of gyroscopic effects that we had neglected in order to decouple these equations, the longitudinal and lateral equations. Okay, let's go on to the third type of coupling, and that is aerodynamic. Okay, so this one is maybe a little bit harder to see. This came about in our equations for the force in the XYZ direction and our moments about mx, my, and mz. So these are our aerodynamic forces and moments. These include thrust. And when we evaluated these, we dropped any aerodynamic derivatives that were not symmetric. And so let me show you, let me just write down 3 common aerodynamic derivatives that are not symmetric that are also commonly non-zero. One of those is CL alpha. So this is your change in rolling moment with respect to angle of attack. Now for a perfectly symmetric aircraft with the geometry is symmetric and the propulsion system is perfectly symmetric, then you don't have a change in rolling moment with respect to angle of attack. But you could if you have some asymmetry there. And one of the asymmetries that is very common is just a single is an aircraft with a single propeller. So you have that single propeller usually on the center line, but that's got a direction of rotation that will create some asymmetries in aerodynamics as you change angle of attack and side slip. So for example, Cn alpha, this is our change in yawing moment with respect to angle of attack. If you remember when we talked about propellers, that as you change the angle of attack of a propeller, that will create a yawing moment. And so our change in yawing moment with respect to alpha would be non-zero if we just have a single propeller on there. Same with change in pitch with beta. So these are three of the maybe most common derivatives that are not symmetric, or excuse me, that couple longitudinal and lateral aerodynamic parameters. And we had assumed that those were zero in order to decouple these equations in our previous development here. Okay, and then for the final type of coupling here is what I'm going to call nonlinear. Now, we linearize these equations when we in order to decouple them, and just to refresh your memory, what we did there was we chose some equilibrium state. And the equilibrium state that we chose was that P, Q, and R were zero. And so remember, we could write P as some P naught, some equilibrium P plus a delta P. And then Q we wrote as some Q naught plus delta Q. And R was some R naught plus delta R. Now, because P naught, and I'll put knots on these, P naught, Q naught, and R naught, our equilibrium state we assumed was zero, that knocked out all of these three terms. And so when we plugged these into these equations here, you can see terms like this, like Q times R that showed up. Well, Q times R, when we linearize this, just turned out to be delta Q times delta R. So these are deviations from our equilibrium state that are really small. And so we said any time we had something small times something else small, we were just going to drop that term. And so we dropped out actually everything in these parentheses over here, because all of these are nonlinear terms. All of these have rotation rates that are either squared or multiplied together. And so because all of these were just the delta values, we dropped all of those terms. And so actually, our final pitching moment equation was just this equation right here, which is really quite simple. And we had neglected the angular momentum tensor, as well as all of these nonlinear terms over here. Okay, so that happened because we linearized the equations. So what did we lose by doing that? Well, let's look at a common example here. This first term right here, and I'll just circle that in blue here for a second. So this term here is can be a term that's really important in the dynamics of an aircraft. So this says that when there's a large difference in our inertia about the z-axis and the x-axis, then this term can be important. So this is common on fighter aircraft. Actually, they tend to have, or not just fighter aircraft, but in aircraft in general. Generally, the inertia about the z-axis is much greater than the inertia about the x-axis, and so we've got a large delta here that we're dealing with, and now fighter aircraft. Now, luckily, most aircraft don't have significant roll rates. Okay, so or roll pitch or yaw rates. So, airliners or whatnot that most of us travel in, the rates, pitch, roll, and yaw rates that we see over here are very small. And so the dynamics due to these terms over here is usually really small, and that's why we were able to drop them. But for fighter aircraft or for stunt aircraft, they can have significant roll rates. So that's P, for example, here. So let's say now that this term is significant, we've got a significant roll rate, and now as long as R, which is our yaw rate, stays exactly zero, this term won't matter. But if we begin to yaw the aircraft just a little bit, because P and the difference in these in these parentheses here are significant, that can create a significant pitching moment. So notice that this is in the second equation here. That's our pitching moment equation. And so this will create a pitching moment if we have a large difference in these inertias. We're rolling at a significant rate, and then we just need a little bit of yaw, and we suddenly get a significant pitching of the aircraft. So this is maybe a little bit counterintuitive because we're talking about roll and yaw right here, right? So we're rolling at some rate, we get a little bit of yaw, but what happens is it creates a pitching moment. So this is, again, these two terms are lateral. Roll and yaw are both lateral, but it creates a longitudinal motion or a longitudinal moment due to this term right here. So this was not really well understood, even at the beginning of World War II, because of the simplifications that people had made to these matrices in order to solve them. These coupling terms were not really understood, especially these nonlinear terms. And so, for example, in 1944, on December 10th, there was an aircraft called the German HE-162 that it was only 4 days after its maiden voyage, and it was doing a high-speed roll, and the aircraft disintegrated. And basically, we can see that if you're rolling high speed and you just get a little bit of yaw, you suddenly have a large pitching moment. And the problem with a large pitching moment is because, it depends on the aircraft. See, a lot of aircraft are very stable in pitch, and so if it got a large pitching moment, some aerodynamic pitching moment, it may be able to recover depending on its pitch stability derivative. But fighter aircraft have very low pitch stability because they need to be maneuverable. And so you combine that with this pitching moment from roll, and now the aircraft can have a rapid change in angle of attack. It can pitch up rapidly or pitch down and change the angle of attack rapidly, and that increases the lift on the main wing, right? So our lift is proportional to our angle of attack. And so as you increase that rapidly, you have a large change in lift, and that can exceed the load limits that structure was made for. And so now you can understand why that fighter might have broken up because of this high-speed roll. So this is a phenomenon that was not well understood until later when they started to include these nonlinear terms in the dynamic analysis. So that's just an overview of some of the types of coupling that you can see in these equations. Again, we just step back to the fundamental pitching moment equation here. Excuse me, not pitching moment, but moment in general from Newton's second law, and included these nonlinearities in inertia, also the gyroscopic coupling here, the aerodynamic coupling that can happen in our terms, and then also these nonlinear terms. And there are ways to look at the dynamics of this, including all of these terms. And most of these involve flight simulation. If you just integrate these equations directly forward in time, you can include all of this information. But there are also other ways to still linearize these equations and capture some of these nonlinearities, some of these coupling terms, even in linearized equations. And in a future video, like I said, I'll go through that process.